Hi, I am Yi-Chen Lu. I am glad to present our recent work at NVIDIA named LEGO Size, LLM-enhanced GPU-optimized sign-off accurate differentiable VLSI gate sizing in advanced nodes. First, I would like to give some motivation and key idea about this work. The reason we are tackling gate sizing is that it is used repetitively across the entire EDA flow from synthesis to sign-off. However, in advanced nodes, gate sizing in commercial tools has become extremely time-consuming, mainly due to the complex design characteristics and the vast amount of choices of library cells, which significantly enlarge the design space. For example, in the commercial 3 nanometer node, there are more than 10,000 of library cells, and traditional approaches, which are used very common, like sensitivity-based optimization, would not scale. So in this work, we think large language models can help alleviate the burden of gate sizing in advanced nodes. Our key idea is that each timing path can be considered as a sentence as in languages, where library cells naturally as words. Therefore, path-based sizing optimization problem can be thought as a sentence-to-sentence translation problem. And the success of LLMs in other fields has given us hope that with enough data and compute, we can train a large language model that understands the PD language. And in this work, we aim to explore this idea. Before diving into the details of the paper, I want to illustrate the four key philosophies of this work. First, although we believe LLM can help, but we do not believe we can simply apply open source, publicly trained LLM models for PD tasks, since they are probably not trained with our technology and design information. In contrary, we believe we need to define our own PD tokens, which in this work we consider library cell name as the base tokens for the model, as illustrated in the top right figure. As shown in the figure, for each library cell, we extract three tokens denoting the gate type, the drive strength, and then the VT. Each of the tokens will have its own trainable high-dimensional embeddings. And beyond the token embeddings, we also include a trainable function embeddings associated with each lib cell, where the lib cell belongs to the same function, as shown in the figure here, will have the same function embeddings. The goal of language modeling is thus to train these two embedding tables into meaningful representations. Now we move to the second philosophy, which is inspired by the limitation of the previous work, Trend-Sizer. Although Trend-Sizer pioneers the use case of the transformer architecture for VLSI gate sizing, it is not adopting a language modeling approach at all. Instead, just like many other machine learning applications, Trend-Sizer does not operate on string-based tokens and requires manually defined features as inputs. However, the most critical drawback of Trend-Sizer is that its prediction is not exact. As illustrated in the bottom right figure here, due to the fact that different gate function has different number of library cells in the library, and due to the fact that machine learning models require a fixed number of output heads for predictions, Trend-Sizer naively performs the binning strategy by uniformly categorize the library cells for each gate function into 50 bins. The drawback of this approach is self-evident, that the model cannot really learn meaningful bin ID because the ID for one gate type, for example the buffer type, may have a totally different representation of the ID for the mux type. Therefore, in this work, we believe we need to leverage language modeling for exact gate type prediction. The third philosophy of LEGO size is that we realize autoregressive approach may not necessarily be good for a VLSI task. It is computationally inefficient and easily driven from one prediction error. Hence, in this work, we aim to explore encoder-only large language models for VLSI gate sizing. And finally, the success of LLMs in other fields has taught us that warming up the model with self-supervised tasks is very critical to the success of the downstream task. Hence, in this work, we aim to bring self-supervised learning into PD by defining domain-aware pre-training tasks. This slide gives an overview of the entire LEGO size framework, which is a multi-stage framework with 3 stages. Before diving into the details, I want to first emphasize that in this work, we are not only using string-based tokens for language modeling. We also extract design-related features and fuse them with the token embeddings as the inputs to the LM model. The features are extracted from different levels in terms of ping, cell, and path, which are fused with input projection layers and encoded by a graph transformer model, as shown in the figure on the left here. The graph transformer model is expected to give a global design view to our path-based optimization task. Note that although our model performs path-based timing optimization that takes one path at a time, we do incorporate the neighboring information to make the sizing prediction decision. The training of the framework is separated into self-supervised learning and supervised fine-tuning, or SFT in abbreviation, where the ultimate goal of the SFT is to predict how much slack improvement the input path will achieve and what are the final library cells to make this improvement happen. The predictions of the library cells in terms of probabilities are further refined by a graph-based differentiable STA engine. Finally, I want to emphasize that the benefit of tokenization, which can be summarized in the equation below, where the symbol here represents the Cartesian product, meaning that every element of one set is to combine with every element of the other set. This equation implies that we only need to use a small amount of tokens to represent a vast amount of words, or library cells in our case. In reality, our technology has more than 10,000 library cells, and it only requires us to use 300 tokens by following this tokenization strategy. One of the innovations in this work is the design of a CMM-based model to encode library timing tables. Particularly, we concatenate the timing tables related to a library arc into 3D tensors, which we focus on the transition and delay tables separated by rise and fall. And then CMM filters are applied to perform convolution across this concatenated 3D table tensor. In analogy, just like an image, we have RGB 3 channels. We have 4 channels per library arc in our framework. This strategy effectively captures the locality of the delay or transition values, as the neighboring elements are usually indexed by similar range of inputs. The final encoded table information is combined with the features and embeddings as mentioned in the previous slide as the inputs of the LLM model. In this work, we devised 2 self-supervised tasks to pre-train or warm up the LLM model before supervised fine-tuning. Note that this self-supervised pre-training does not require any optimization labels, which means we can open any database in the company and collect the timing path and their features to warm up the model. One of the self-supervised tasks is the cell-based arrival time prediction task, as shown in the figure on the left here. Given a timing path, we train the model to predict this stage-based arrival time increment along the path. The goal is to have the model to pick up the timing concept by using the RC features and the associated library information. Another task is the mask token prediction task, which is commonly termed as MLM. This is achieved by randomly masked out a token and have the model to reconstruct it. As shown in the figure, at the second library cell, the drive strength token, B3, is replaced by a mask token, and the model will try to leverage the information it has to reconstruct it at the output. In experiments, we find this MLM task very effective to let the model understand the timing context, because the model is given enough hints to really understand the timing path information to reconstruct these mask tokens. We evaluate the effectiveness of self-supervised pre-training by visualizing the token embeddings. In both figures, a circle represents a library cell, and the number denotes the function. Figure on the left is only trained with the mask token prediction. We can see the library cells with the same function are already tending to group with each other. Figure on the right is trained by both mask token prediction and the arrival time prediction task. We see that library cells form more distinct clusters than the left figure. As aforementioned, although we are doing path-based optimization, we leverage a graph-based model, particularly a graph transformer, to encode netlist information for path-based decision. As shown in Figure A, a critical path that we aim to fix, we define the valid recycled field as its local 3-hop neighborhood for the graph transformer model to encode. And since the graph transformer model requires a positional encoding representation for each node, in this work we leverage the random walk-based positional encoding, where we define a random walk operator as the adjacency matrix A normalized by the degree matrix as shown in the equation here. And the diagonal elements in the power of k of this random walk metric naturally represents the probability of coming back to each node after performing a k-step random walk. And finally, as shown in the figure C, with the initial node features and the corresponding positional embeddings, we adopt a linear attention mechanism to reconstruct final node embeddings, which are not only passed to the LLM model, but are directly leveraged to perform gate sizing prediction tasks as well during the fine-tuning stage. In the experiments, we observed that the prediction results achieved by our graph transformer model outperforms previous GNN-based work like ECO-GNN. Now we illustrate the detailed architecture of the modeling part of LEGO size. Particularly, I want to focus on the rationale of slack conditioning in the middle during supervised fine-tuning step. This is a strategy which we find very helpful in improving the prediction accuracy and to further enable precise PPA trade-off. The idea of slack conditioning is that during training, we let the model know in advance how much slack will be improved of the given timing path subject to the final achieved library cell. We imagine by having this information, the model should learn how many gates and how to size them to achieve the desired slack target. Note that during training, this slack conditioning is trained with ground truth labels in a teacher forcing manner, which means we put this label as input features to the model. But during inference, we use the slack hat predicted slack conditioning value to condition the model to inference the library cells. And finally, the dashed box on the right shows a detailed illustration of how we construct the final library cells. Since our model is operating on token basis, each prediction of a token is governed by a probability distribution over its valid options. We thus apply a Cartesian product for every 3 tokens along a path to reconstruct the probability distribution of the final library cells. We normalize the probabilities of the top K library cells and further leverage them to be refined by a differentiable STA engine. The key idea of our differentiable STA engine for probability refinement is on the delta-based approach. As illustrated in the left figure, assume cell G is selected to be sized by the model to a different library cell. We leverage the estimate ECL command from a commercial tool to evaluate the subgraph timing impact subject to the top K library cells predicted by the LN model. Then we adjust the original delay of the arcs related to the cell G with a new estimation subject to each LN predicted probability. And finally, with a newly annotated delay in terms of expected value, we leverage custom torch 2-dot kernels to perform timing propagation in a differentiable manner, where the arrival time at each output pings are merged from the input pings through a log sum exponential operator rather than the commonly used max operator. This allows us to calculate the gradient smoothly in the backward process, where the gradient of each arc, in this example Z, AZ, and BZ, is proportional to its contribution of the arrival time. This slide illustrates the complete differentiable gate sizing process. First, we want to emphasize that our STA engine adopts a different philosophy from common ones, where we directly clone the arc delays from a commercial tool and initialize a timing graph from it. Then we develop our own custom kernels to perform arrival time propagation in a differentiable manner. In the end of the day, the calculated TNS is differentiable to the probabilities of each library cell option of each gate with the chain rules as shown in the figure. Note that thanks to the advancement of modern deep learning toolkits like PyTorch, the cumbersome chain rule update is handled by the backpropagation process on the computational graph. Hence, we only need to define how the gradient propagates at each timing level as highlighted in the purple box. Finally, a great benefit of this probability refinement using the STA engine is that it removes the path-based ambiguity of the path-by-path sizing formulation. Since one cell can sit on multiple validating paths, with our engine, we refine the probability on a graph-based level, albeit we may experience timing path symmetry that may introduce overfixing due to the nature of GPA analysis. In the experiments, we verify our model in a real-world industrial setting. We collected 21 physical design implementations originated from 5 high-performance RTL with different PNR recipes. We gathered around 28 millions of timing paths with optimization labels from a commercial sign-off tool. We first pre-trained the LEGO framework using the self-supervised learning task as aforementioned, where the pre-training takes around 1 week with 800 GPUs. Note that during pre-training, no optimization labels are used. For validation, we only test the model on on-scene implementation, where we observe that we can achieve better optimization results with much faster runtime. Here we show two ablation studies. On the left, we try to understand how much benefit does the differentiable STA engine bring. Particularly, we leverage different combinations of predictive components as well as previous works to perform sizing predictions, where we observe that without the differentiable STA engine, we at most achieve on-par optimization results as the reference tool. Another ablation study is shown on the right, where we select 3 timing paths. On the x-axis, we vary the slack conditioning amount to the model and verify the final slack achieved by the library cell prediction. We observe that in general, the model is trained to understand the conditioning. Now we summarize our work, which we have shown that by properly defining tokens, language modeling techniques can be well applied for PPA optimization in PD, and they are effective for handling large and complex design space. We also show that how GPU-accelerated differentiable optimization techniques can be used for large-scale optimization in PD. In the future, we plan to improve LEGO by optimizing more PPA objectives simultaneously and also handle multi-scenario optimization. Thank you for listening.